Welcome students. Today we will be talking about the next cyclic accelerator, that is the Betatron. It is a device or an accelerator which is used to accelerate electrons or beta particles. So we had discussed about the cyclotron. Cyclotron is a device which can accelerate charged particles to high energies. But the limitation of a cyclotron is that when the particles they attain relativistic speeds, a cyclotron can no longer effectively accelerate the particles because the cyclotron condition is no longer valid. Means when the particles attain relativistic speed, their relativistic mass increases and the condition is no longer satisfied. So the cyclotron cannot accelerate electrons effectively, or it can't accelerate electrons because electrons being light, they attain relativistic speeds very easily. So this accelerator called the Betatron was designed specifically to accelerate electrons to high energies. High energetic electrons, we call them the beta particles, so the name Betatron. So it was first built in 1940 by D.W. Kirst. It can accelerate beta particles through very high energies. So the basic principle of operation of a Betatron is the principle of electromagnetic induction, which is similar to a transformer. So all of us, we know a transformer, it consists of two coils, a primary coil and a secondary coil. An alternating current flowing in the primary coil, it generates an alternating magnetic field. So the flux linked with the secondary coil changes because of the changing magnetic field, and hence an EMF is induced in the secondary coil. Similarly, in the case of a Betatron, what happens is there is a primary coil surrounding an electromagnet. This is the basic construction of a Betatron. All these figures, they show the basic construction of a Betatron. So it consists of a chamber, donut shaped chamber, which is placed between the poles of an electromagnet. So these are the poles of the electromagnet. This is the side view, cross-sectional view. This is the top view. So what happens? The electrons, they go round and round the chamber in an orbit of constant radius. It is placed between the poles of an electromagnet. So this electromagnet is energized with an alternating current having a frequency of around 60 to 100 Hertz. So because of this current flowing in the primary coil, the electromagnet generates a time varying magnetic field. As a result of this, the flux linked with this chamber, it changes and it induces an EMF in this because of the changing electric field. So what happens in a Betatron, changing magnetic field rather. So what happens in a Betatron is electrons are injected into the chamber with a particular initial velocity, and any charged particle moving in a magnetic field, it moves in a circular path. So basically the electrons being injected with a particular initial velocity under the influence of the magnetic field that is produced by the electromagnet, they move in a circular path. So and it goes round the chamber and completes the path. So this is nothing but like a current loop. The electrons or charged particles going round and round, that constitutes a current loop. So this current loop itself acts like the secondary. So the primary of the transformer principle here is the primary coil surrounding the electromagnet. Because of that, changing magnetic field is produced. So the magnetic field linked with the electron orbit, it changes. That is the flux linked with the orbit, it changes. So this acts as the secondary coil, as a result of which an EMF is induced. So this induced EMF generates a force which accelerates the electrons. So the basic idea behind a Betatron is that as the particles are accelerating, we know if the magnetic field remains constant, higher speed particles, higher velocity particles, they should go in circular orbits of higher radius. So what should happen? The electron should spiral out, it should go out of the chamber. It should keep on going round and round in orbits of higher radius. But if that happens, the Betatron can't operate. So what is done in a Betatron is a condition is achieved such that all the electrons, they move round in circular orbits of constant radius. So that condition is known as the Betatron condition. So that is achieved in a Betatron to effectively accelerate electrons to very high energies. So as we talked about, it works on two basic principles. The changing magnetic field, it induces an EMF rather. Electrons moving in a magnetic field move in a circular path. The particles move in circular path of constant radius. The condition under which this is achieved is called the Betatron condition. Now let us see how we can derive the Betatron condition. So let's do some simple calculation regarding to find out the Betatron condition. So let phi be the flux linked with the electron orbit that we are talking about. Let us say that the orbit has a radius of r. The electrons are moving round in the chamber, or to say in an orbit of radius r, and let phi be the flux linked with this whole area of the orbit at any instant of time, and this flux it changes because the magnetic field is changing. So the EMF induced in this orbit, we can call it epsilon, is equal to d phi dt. So if E is the EMF, then the work done by this EMF in taking round the particles through the circular path of radius r, the work done, we can write it as W, that is equal to 1, let us call it W1, is equal to E into epsilon, that is equal to E d phi dt. This is the work done by the EMF in taking round the particles through this circular orbit of radius r. Now again, let us say that we are talking about the electrons experiencing a force because of which it goes round the circular path. So let F be the force which the particles are experiencing. Now the path length of this circular orbit is twice pi r. So the work done from this case, we can write it as W2, work done by this force. We don't know what is this force till now. The work done by this force in taking round the particles through this electrons through the circular orbit of radius r is equal to force into the path length, that is twice pi r. So these two works should be equal. Therefore, we can write W1 is equal to W2. So we can write therefore F into 2 pi r, that should be equal to this E d phi dt, right? Implies we can simply write F to be equal to E by twice pi r into d phi dt. So this gives us an expression for the force experienced by the electrons while going round the circular path of radius r. Now again, the electrons moving in the circular orbit of radius r, they will experience a centripetal force, and they are moving in the orbit of circular in an orbit of radius r, in it they are moving in a circular path because of the force it experiences due to the magnetic field linked with the orbit. So now let us say if B is the strength of the magnetic field linked with the orbit, if B is the strength of the magnetic field linked with the orbit, and the direction of this field is perpendicular to the path of the electrons, that is perpendicular to the velocity. So, the force experienced by the electrons due to this magnetic field will be equal to QVB. Here Q is equal to E, the charge of the electrons, V cross of B. So, that is VB. So, this is the force. So, this force, it is giving rise to the centripetal force, which keeps the electrons in its circular path. So, that should be equal to mv square by r, which is the centripetal force. Any particle of mass m, let us say m is the mass of the electrons, moving at a velocity v in a circular path of radius r. So, from this relation implies we get v and v will cancel out. So, we get an expression for mv that is equal to ERB. Now, what we are saying is that this magnetic field, it changes with time, and also hence because of the force experienced by the electrons, the velocity also changes with time. So, this is mv is nothing but the momentum of the electrons. So, this momentum also changes with time. So, we can find an expression for the force experienced by the electrons, which is giving rise to the change in its velocity. So, this force we can write it as d mv dt, the force experienced by the electrons. That will be equal to Er. We know that the radius we need to keep it constant. So, we are keeping it constant. So, we are putting it as dB dt. So, we have two expressions for the force. One, here we are getting a force experienced by the electrons, which is due to the changing magnetic flux in terms of the changing magnetic flux, and here linked throughout the whole orbit, and here we are finding it alternatively through the Lorentz force or the force experienced by the electrons due to the magnetic field. So, these two expressions for the force experienced by the electron should be equal, and here we are keeping r to be constant. So, the condition that we will obtain from this is what is known as the Betatron condition. So, we have two expressions for the force. So, this should be equal. So, therefore, we can write Er dB dt, that should be equal to E by 2 pi r d phi dt. So, if we simplify this, implies we get d phi dt, E and E can cancel out both sides, is equal to 2 pi r square dB dt. Integrating this expression, we get implies phi is equal to 2 into pi r square b. Now, B is the magnetic field linked with the electron orbit. B is the magnetic field linked with the electron orbit, and pi r square is the area of the electron orbit. So, this is pi we are talking about, this is r. So, pi r square gives us the area of the electron orbit, and B is the magnetic field linked with the orbit. Phi is the flux throughout this orbit. So, these three things we need to remember. B is the magnetic field linked with the orbit. Pi r square is the area of this orbit, and phi is the flux linked throughout this orbit. So, pi r square into B gives us the magnetic flux linked with the orbit. Now, let us say that B dash, suppose B dash is an average field average magnetic field which is uniform throughout the orbit, of the electrons, then we can write phi to be equal to the flux throughout the orbit if the magnetic field is uniform throughout the orbit is equal to pi r square b dash. Therefore, we can write pi r square b dash is equal to twice pi r square b. So implies from this we get b is equal to half of b dash. So this condition is known as the Betatron condition. So here what we have is, suppose B dash is the average magnetic field linked throughout the orbit, means throughout the area of the orbit, if the magnetic field is an average field which is uniform throughout the orbit, and B is the field at the orbit, then the Betatron condition is the field at the orbit is half of the average field throughout the orbit. In terms of the magnetic flux, we can write it as pi r square b dash, where b dash is the average field. So we are talking about, this is the orbit. So the average field linked throughout this orbit, if we say that the average field throughout this orbit is b dash, the flux linked with this orbit is pi r square b dash. The flux linked through this orbit is throughout the area of the orbit is pi r square b dash. We are calling it phi dash. And the Betatron condition then becomes phi is equal to twice phi dash. That is the flux through the orbit is twice the flux enclosed by the orbit. The flux, magnetic flux through the orbit of the electron is twice the flux enclosed by the orbit if the magnetic field were to be uniform over the whole area. So this condition is known as the Betatron condition. So that is achieved. This is called the Betatron condition. So this condition needs to be achieved in a Betatron so that the electrons, they move in a Betatron in orbits of constant radius. So this is achieved by specially designed pole pieces where the magnetic field is greater at the center of the orbit than at the circumference. So the whole design of the Betatron goes into achieving this condition known as the Betatron condition. That is, the flux through the orbit is twice the flux enclosed by the orbit if the magnetic field were to be uniform over the area. This graph, it shows the variation of magnetic field with time. So in a Betatron, the electrons are injected into the chamber at the point when the magnetic field starts increasing. So these are the points where the electrons are injected into the donut shaped chamber. So as the magnetic field increases, it induces an EMF which accelerates the electrons. So by the time the magnetic field starts from here and reaches here, the electrons may go round many times within it in its orbit. So at these points, the electrons are ejected out, deflected from their orbit, and they are made to hit their targets. If the electrons are allowed to stay in the chamber beyond this point, what will happen is the direction of the rate of change of flux becomes negative, means the flux starts decreasing and the EMF is induced in the opposite direction, which will retard the electrons. So basically in a Betatron, the Betatron condition is achieved. The electrons move around in circular paths of constant radius, and the electrons are injected into the chamber at the point when the magnetic field starts increasing, and they ejected out of the chamber when the magnetic field it reaches its peak. So this is all about the Betatron. So we have talked about what is a Betatron, what is the basic principle of operation of a Betatron. We have discussed about its condition, construction, and then how the Betatron condition is achieved, the theory. Then we can talk about 1 or 2 points of its advantages. Basic advantages: it can accelerate electrons to very high relativistic speeds, and also electrons, or for that matter any charged particle moving in relativistic speeds, they emit energetic X-rays. So Betatron also is a good source of X-ray. And even the electrons, they can be allowed to hit targets which will also generate, what to say, X-rays. So this is all about the Betatron that we had to discuss. So we'll talk about the next accelerator in the next video lecture.